We discussed about the fuel cell last time, and this is what we call salinity gradient power. This system does not exist yet. There's no big plant, no big installation, but there is a lot of interest, a lot of attention to the problem, because in principle the salinity gradient power can cover more than 20% of the global energy that we will need in the future. So it's competing with, I don't know, with nuclear power, with wind power, with solar energy, etc. So quite interesting. The problem is that is totally related to the existence of membranes, appropriate membranes. First, when we will have the membrane, there's a lot more to be done, but for sure, without the appropriate membranes, there will be no possibility also to test the potentiality. The idea is not new. The idea is not new because if you go in the literature and you read a paper on Journal Membrane Science in the 70s by Professor Sid Loeb, the same professor that invented reverse osmosis, he was already mentioning about PRO, pressure retarded osmosis, as a way to produce energy. So the idea was is not today. The problem is that we tested. We've been also working with him at that time in the late 70s, but the membranes available at that time were not appropriate at all. We had lights in switching on, but for 10 minutes, 20 minutes, half an hour, and afterwards slowing down. Because also having some membranes, as the good reverse osmosis membranes, there are some problems related not to the membranes, but to the efficiency of the system for what concerns the control of concentration polarization, and particularly a new form of concentration polarization, the one what we call internal concentration polarization, in the spongy part of the porous membranes produced for reverse osmosis. So there was problem and less interest at that time. However, keep in mind that today this system works in nature. In nature, when nature has to produce energy, is using osmotic phenomena. Nature was not using osmotic phenomena to produce water. It's using osmotic phenomena to produce energy, to the point that when we had the idea to use osmotic phenomena, we use osmotic phenomena to produce water, and we had to call reverse osmosis, because it's just the opposite of what normally happens in nature. Today, if people want to use osmotic phenomena to produce energy, as in nature, this can be a good idea, and people have to work. If you want to produce osmotic and using osmotic phenomena, direct osmosis, what we call forward osmosis, to produce water, this is a little bit more tricky. Nature is not using this phenomena to produce water. To produce energy, yes. The basis of this salinity gradient, that we also call blue energy, is just related to the osmotic process. So that is the basis, and it's related to the fact that in nature we have a lot of salty water, seawater, or brackish water. Sometimes not only sea. Keep in mind there's a lot of salty water in the lakes. If you go to China, there are some lakes that have more salts than the sea. And fresh water, river normally, or any kind not salty water, and also we are plenty. If you check about the Gibbs free energy of the salty water and the fresh water, there's a big difference. That's the same difference that we have been using in producing electrical energy in the battery. difference in Gibbs free energy of the two systems. Here the same, and we have plenty of seawater and fresh water. When they mix, if they mix in an open system, nothing happens. We are mixing and they will approach a situation which there is homogeneous concentration in any part of the system that you have been creating, and that is what is normally happen. Salty water will diffuse in the fresh water, the system mix, and the concentration will be homogeneous. If you do this operation in a different way, as we have been learning to do in the battery, for example, just trying to concentrate to have the electrons produced in oxidation reaction moving in external line and producing electricity, we can do the same. We can try to make this mixing in a different way, trying to take profit. And that can be just using a osmotic membrane. That means a membrane in which only water can go across. And if you remember the different osmotic phenomena, if you just have a simple system where there is a salty water and fresh water, and the membrane is ideally semi-permeable, only water can go across, the only way to have an homogeneous system with a Gibbs free energy equal in any part of the system is having fresh water entering in the salty water, trying to dilute, because there is no way, there is no salt that can go in the other direction to concentrate the water. The only thing that can happen is the fresh water entering the salty water, and that's if the compartment is closed, you are just creating hydrostatic pressure. You can have pressure, and this pressure can be going to in a turbine and produce electricity. Exactly as it happens in nature. So this is the system. Just to remember the osmotic process. Osmosis is transport of water across a selective permeable membrane from a region of higher water chemical potential to a region of lower water chemical potential. It is driven by different solid concentration across the membrane that permit the passage of the water across, but reject all or most of the solid molecules of ions. Keep in mind that with this most means today, membrane, the one we have not been discussing in this class about reverse osmosis, etc., but in desalination, you heard already, we have membrane with selectivity 99.9. So basically, it cannot be 100% for definition of rejection, in which the rejection is the difference between the concentration of the feed, refer to the concentration of the permeate, but is very high and approaching 100%. In membrane distillation, we can arrive to 100% because the mechanism is totally different. So the osmotic pressure is just the pressure which, if you apply to the more concentrated solution, will prevent transport of water across the membrane. When you have this phenomenon of water going in, and you see that if the compartment is closed, there will be growing in the system of an hydrostatic column, and that is the kind of phenomena that you are observing in reverse osmosis. In reverse osmosis, we have a system in which what is happening, let's start from the osmosis. Normally, if the separation between the fresh water and the concentrate solution between the feed can be just fresh water and the brine can be salty water. If there is no membranes, and if the system is just a porous system, the two hydrostatic columns will have the same level. There is no pressure here. If you have a traditional osmotic phenomena, today you call this forward osmosis, but there's nothing more than just osmosis. What is happening is that to have the equal chemical potential, to equal Gibbs free energy basically in the system, what is happening that the fresh water will go across the membranes, will penetrate here, trying to dilute, to decrease the chemical potential here to make equal to the one of the water. Doing this, we create an hydrostatic column, which make pressure on the surface. At one point you will see that the system arrives to a quasi-state. That means seems to be in equilibrium. This system will stay against this one. This apparently violate the traditional capillary system in hydraulics. They tell you that the water is always, if you have two columns and they put together, and one is higher, the other one is lower, immediately they arrive to the same level. There is a mechanical equilibrium that you create immediately. Not here. And no, an hydraulic engineer does not understand what is happening. That's violate basic principle that everybody trusts. But the difference is that here there is a membrane, a system semi-permeable in which only water can go across, no salts. So that's the only way in which you can try to have the same chemical potential on both sides. When the system arrives to equilibrium, that means there is no more change here, if you measure this level, this is exactly the difference, what we call osmotic pressure. The delta P, that is the difference between the osmotic pressure of this solution to the one on the other side. And that is what you can measure in this way, the osmotic pressure, this difference, because that's exactly the one that we call osmotic pressure, which is given by very well-known equation that you have to remember, that is equal to the equation of the ideal gases. That is, this pi is equal CRT. That means the absolute temperature, R, gas constant, and universal gas constant, and the concentration. That's because what is happening here is very, very similar to the behavior of a gas. We have atoms, molecules in the solution, and they just are mobile. They can, different than a gas, they're not the same speed, etc. And they just have they move to the surface. They just have a crack on the surface. They have a force for a unit of the surface, and that is the pressure. So that is the difference of the ion present here and here that is creating the osmotic pressure. So that's what we call osmosis, or today forward osmosis, in which the water is going in this direction, which means here has to be very high concentration and here low concentration for having a significant driving force. What we call reverse osmosis normally is just the opposite. We were looking for having more water. The idea was, where is the water? The sea. The sea is salty, so the only thing to be done, try to remove the salt from the sea. So we invented reverse osmosis. And that was invented in the middle of the 60s. And today, as you know, is a dominant technology, and we will discuss about. But the problem in this case, you just apply a driving force, an hydrostatic pressure, on the salty water, and this pressure has to be higher than this delta pi, otherwise water will go in the other direction. So what you have to do, if, for example, if you know the concentration of this solution, you can calculate the osmotic pressure, and you can apply on this solution an hydrostatic pressure higher than the osmotic pressure, which is moving the water in this direction. So if, for example, in seawater, this can be 25 atmosphere order of magnitude, 0.5 molar. And that one here, if you apply something less than 25 atmosphere, no water will go out. Still water will go in. If you apply here 26, 27, 50 atmosphere, you have an effective driving force overcoming the osmotic difference, moving the salt out in the other compartment across your membranes. These membranes is exactly the same that you are here. It's a membrane semi-permeable, only water can go across. If you pressurize and if you don't break your membranes, only the water can diffuse across the membranes. Okay? And that's what we call the reverse osmosis for producing clearly just water from the sea, desalination. in between, we can have what is called a pressure-retarded osmosis. As you can see here, there is a system in which you are applying a pressure here which does not overcome the osmotic pressure, so you still have water moving from this compartment to the other compartment, from the fresh water to the salty water across, but with a flux which is lower, that is different from the one that you have here, because that is just lower than the pressure necessary to the extraction. So there is no pressure that you apply here sufficient to move. That is the situation in which this pressure is lower than the osmotic pressure, basically. And that's what we call pressure-retarded osmosis. Pressure-retarded osmosis, as you see here, is a system in which the water is again moving from this compartment to this compartment. So again, pressure-retarded osmosis has been invented to produce energy, as in nature. Nature is working on a very situation, pressure-retarded osmosis. Still, you can pressurize here. You are increasing this level, and you can produce energy, not for producing just water. Because also if there is some fresh water, as in FO entering here, that's always a situation in which there is a salty water. So you mix fresh water with salty water. So pressure-retarded osmosis is, again, as in nature, a way to produce energy, not to produce fresh water. So if people want to produce fresh water, don't use this system. Today there is some confusion sometimes, but that's the situation. Reverse osmosis uses hydraulic pressure difference as the driving force for the transport of water to the membrane. In osmosis, forward osmosis, this pi, we use the osmotic pressure driving force resulting concentration of the feed stream and dilution of highly concentrated stream. That's what is called a draw solution. And that is one of the big problems that exists in this system, because for having a significant flux, this solution has to be very high osmotic properties. And so if you want after to separate this draw solution from the water that you have been extracting, this is not a minor problem. And you will see there are some way of doing, but that is one of the big limit to the process for just producing water. Pressure-retarded osmosis can be viewed as an intermediate process between FO and RO, where hydraulic pressure is applied in the opposite direction. The hydraulic pressure still applies to the osmotic pressure gradient. However, the net water flux is still in the direction of the concentrate draw solution, exactly as here. So these are the three osmotic processes that exist. And when we discuss about the osmotic phenomena, that is the situation that you can have. If you just plot the water flux as function of the pressure, delta P, you can have a situation in which delta P is significant, is higher than the osmotic pressure, so you are in this region, and the water flux is increasing delta P. You can have one point in which the delta P and delta pi are equal, nothing happens. There's no flux across. There is another region in which the water flux is negative, is going in the other direction, in which basically the delta pi of the system is lower than the delta P. And that's a situation in which there is just the opposite, just osmosis here instead than reverse osmosis. So this is, this one is the area in which we have reverse osmosis, and that is the area where we will have a forward osmosis where delta P is one of the big advantages, by the way, if you want to see the positive aspect, that we define already direct osmosis when there is no pressure. So you say it's just diffusion. We don't pressurize the system. So in this case, in terms of energy, it's much easier. Mechanical resistance of the membrane can be different, etc. There's no necessity to pressurize. We just diffuse across. This region here is all the region in which we have a pressure-retarded osmosis. In this region here, delta P is higher than delta pi. In all this region, we have delta pi higher than delta P. Okay, that is the situation. So for definition, for normally in forward osmosis, delta P is 0, no hydrostatic pressure. In reverse osmosis, delta P always higher than delta pi, and in pressure retarded osmosis, delta pi always higher than delta P. So that is something that we have to remember, and this equation is very important. This is a simplified equation, by the way, but this equation tells you that the transmembrane flux of water, JW, is proportional, and we learn the value of this proportional, to delta pi minus delta P. In front of delta pi, there is the sigma. It's called also Staverman coefficient. It's giving you, we are assuming that normally the membranes is ideal. Only water is going through. This is not always true, and any deviation from this 100% selectivity is given by this sigma here. However, remember that there is another approximation in this equation. This approximation is the fact that we are not assuming any concentration polarization phenomena. That means when you are looking at this equation, you can measure delta pi if you know the concentration of your solution and the concentration on the feed solution and on the permeate. And you are assuming that delta pi is the difference between the two. That is true, but it's very approximate, because you have to remember that in the concentration we are talking is the concentration at the interface, where the equilibrium from the solid in the membrane phase and the one in the bulk. Now, if there is no concentration, what you measure normally is the concentration in the bulk, assuming that everything is constant, and normally it is, except when there is a membrane and something going across a semi-permeable membrane, because we can build up a concentration profile, in this case, and so the concentration that really controls the process is the one at the interface that in principle we don't know. You have to measure or to predict, okay? So that is the general equation, but we have to control for the quality of the membranes, the sigma, and for the and assuming that there is no concentration polarization, which always exists. So this, we have to modify and to consider the real concentration at the interface that we have to find a way to measure. Now, what is the problem? This is one way, by the way, in which, to give an example, how the system can be realized. That is what the typical forward osmosis process, which in my generation we'll call osmosis. Today they invented a new term because we want to do something new, but it's not new. It's a traditional osmosis. And as you can see here, how it's done. Here you have your membrane system, and on one side you have the feed water, and on the other side you have the draw solution. So what is happening here is that the fresh water is going across and entering the draw solution compartment, which is the one on the other side of the membranes. So you have this feed water, and you have that solution will concentrate, and the concentrated draw solution is entering the other side, and this is the cycle. So on one side you concentrate, and the other side you have what is called product water. So the product water, however, is not just product water, it's a product water in the draw solution. So if you want to use this water that you are extracting from the feed for drinking, forget. You cannot drink these things, because this is a draw solution diluted with the water that you have been attracted. So if you want to use for energy, because you can pressurize this system, etc., as we saw in principle before, is okay. But if you want to drink this one, not drinkable, because you have a draw solution. Now, what is the draw solution? The draw solution has to be a very concentrate system, giving you high osmotic pressure. And there are people working, making research to find the highest, the most interesting draw solution. Normally, the draw solution can be sulfur dioxide solution, mixture of water and some gases, or aluminum sulfide solution, glucose, sugar solution, a mixed solution of glucose and fructose, solution of potassium nitrate and sulfur dioxide. That is the one that people are using, ammonia and carbon dioxide gases in specific ratio, and that are just creating high concentrate, that's ammonium carbonate basically, highly concentrated draw solution of thermally removable ammonium salt. The idea of using this salt, that means ammonium carbonate, that these salts are easily decomposed by increasing temperature. And what you form by the composition of the ammonium carbonate is ammonia and CO2, which can be released easily or recovered. However, the point here is that if this is for making some other operation or for use in some industrial process, is okay. But if you have to drink, before you remove 100% the ammonia and you remove 100% the CO2, the carbonate, not easy. Second, when you put these salts, ammonium carbonate, in the solution, you must be sure that this is to be ultra pure salt, because otherwise, most part, when you buy these products, there is always some contaminants of different kind for a traditional application. And when you decompose, the gases will go in the atmosphere, but the contaminants can be just in the solution. So before drinking, you must be a little bit careful. Anyway, that is one possibility, to have ammonium carbon dioxide gas specific ratio, which create high concentrated raw solution of thermally removable ammonium salt, allowing high recovery of potable water from concentrated saline feeds and substantial reduction in brine discharge from the salination. This is one of the hypotheses which is related to the kind of flow sheet I showed you before. Other possibilities is the concentrate fructose solution, which is also in a way to produce at the end some nutritious drink during for osmosis of seawater. That means the way that if you are using this fructose with the water coming in, at the end the fructose can be utilized. But that's again is the problem if you want to use for this kind of application. In general, the direct application, the traditional application for the osmosis was, for example, in the concentration of juice. If you have to concentrate orange juice or any beverage at relatively low temperature, today it's done by thermal system, so you evaporate the water. This is the way to extract the water from your juice. So years ago already, in the 60s, in the 70s, the idea to produce a concentrate of orange or apple juice, etc., using osmosis was already there. And the problem of concentration polarization was less severe than in desalination, because the cost, the lifetime requested was lower. The cost of if you sell orange juice concentrate, the price is much higher than just selling just fresh water. But so desalination of seawater in principle is possible. Treat industrial wastewater, concentrate leaching, or to treat liquid food in the food industry. That was the one that people have been using more and still are using in some case. The forward osmosis that can be just using for potable reuse in life support system, in demonstration system, I was mentioning as, for example, in the space lab, purifying water in emergency real situation, controlling dry release in the body. This is a lot of applications, in which case the problem I was mentioned are less important. But if you want to control some release of some drugs, etc., this kind of phenomena can be utilized. You have osmotic pump. You have a very, very small pump in which this entering of the water, the change and can pressurize, can move out some drug from a mini pump. And that is based on the osmotic pump that you put in the body for the release of some drugs is based on this kind of phenomena, for example. This is the typical, the one patent that made the starting of some idea to industrialize the system, and that was this, people try to make some real activity. That's the same that I showed you before with this ammonia carbonate, because they were assuming that basically if you just increase a little bit temperature, this one is going in the air, and there will be just fresh water produced here, because all these gases are left. Can be done, but I will never drink this water, by the way, but I suggest to do the same. Don't drink too much of this water. The problem which exists already in the system and will exist in all of the osmotic phenomena is, however, this one. The real problem is what is called internal concentration polarization. We have discussed already, not with you, or for some of you, yes, but we discussed about concentration polarization. We mentioned concentration, polarization, or talking about gases, etc. But basically, the main problem when you discuss with in reverse osmosis. And concentration polarization normally is related to the fact that if you have a certain solution, seawater, that is an homogeneous, the feed is just a solution. By definition, a solution is a system in which any small elementary volume you identify, the property of this elementary volume is the same. The system is homogeneous. There is no diversity in terms of density, concentration, viscosity, color, etc., if you have a real solution. So by definition here, you are assuming that the concentration you have here is the same in all the system. It is not if the system is working in a membrane system, because here we have a system in which the water is going across, but only water. So some of the salts that are not going across will accumulate on the surface. And the back diffusion is much lower than the convection to membrane surface. So the back diffusion here is smaller, and so what is happening here is that some of the salts that accumulate will not be mixed again in the solution, and so we will have starting to have this concentration profile. And this is what we call concentration polarization. The real concentration, when we wrote the equation giving the transmembrane flux, the concentration that we have to consider is not this one, it's this one. The concentration of the different species at the in the membrane phase in equilibrium with the concentration outside at the interface membrane solution. So this is the one controlling the driving force. So if we have this kind of phenomena, this is what is happening. We will have different concentration. This concentration can be high enough that there is no flux anymore. Reverse osmosis has a recovery factor only 50%, because when you increase too much the concentration, with the applied hydrostatic pressure, 30 atmosphere, if you have seawater has an osmotic pressure order of magnitude 25 atmosphere. So you normally apply 30 atmosphere, and you have an effective pressure from the equation we wrote before of a 5 atmosphere, moving the water across. If the solution is no more seawater, but is becoming no more 0.5 molar, but 5 molar, the osmotic pressure is going to be roughly 50 atmosphere. And with the 30, we have 20 effective atmosphere acting as driving force in the other direction, just moving fresh water in the system. So the system does not work. That is normal concentration polarization taking place at the interface of the membrane solution. But when we are working in osmotic process, not reverse osmosis, but just in forward osmosis, you have another problem. That in the other problem you have the draw solution here, a salty, very high concentrate salty solution on this side. And so what can happen here, that you can have also some flux of the salts from this side in the other direction. And today and yesterday we were using all these membranes here to be effective are asymmetric membranes. Asymmetric means that the thickness of the dense membrane where the solubility diffusivity system is working is very, very thin. Much, much thinner than the membranes you have in your hands. In your hands you have a membrane with this thickness, 100 microns. If you want to operate with 100 microns membrane, the flux will be very, very low, because the flux is reverse to the thickness of the membranes. If you make an asymmetric membrane where the 100 microns will be 95, just a porous support, and 2, 3, 5 microns, the dense skin where the selectivity exists for the solubility diffusivity, the flux will be 2 order magnitude higher. Will not be, if it was 1 before, now it's becoming 100 times higher for the equation that we wrote down before. And that's what happened in reverse osmosis. In this case, happening something different. In this case, the salt is moving in and is penetrating in the spongy part. In reverse osmosis, you can control this concentration by cross flow, high velocity cross flow, by steering, by back diffusion, by different way. And as you learn, basically, we operate with no more than 10% difference today between the concentration here and in the bulk. In reverse osmosis, with asymmetric membrane where only water is going this direction, and a very, very marginal amount of salts, 99.9, so nothing, and also if it's going this direction, so we can flush out, we can move out. In this case, it's entering here, and when it's arriving on the dense skin, it's not going through. So the salts accumulate in the spongy part. No way that you can, using increasing cross-flow velocity, Reynolds number can be 30,000, etc. Mass transfer in the spongy part of your membranes is zero, basically. So the salt that is entering here will block at the interface and will accumulate. And it will be very, very complicated, expensive, etc., to remove the salt. So you are increasing the concentration inside the spongy part. That's what we call internal concentration polarization. How you can solve this problem? Not easy. The best way for solving the problem should be if you are able to make RO membranes with no porous part, only the dense skin. That means 0.1, 0.5, 1 microns membranes with the mechanical properties able to operate in the condition typical of reverse osmosis. No one has never been able until now to do something similar. What we are doing today, that if you are working, taking care of the flow dynamics, for example, working always in, not in these two fluxes, as you can see here, they are always in counter current, no co-current. We always, if this feed is moving in this direction, on the draw solution is moving in the other direction, trying to have as much as possible always a good driving force. This can minimize this kind of phenomena. You can find materials with sufficient open porous support that it's a little bit easier to remove the salts, etc., etc. Somebody has to invent a new way of doing. For example, if you find here something that will tend to reject the salts, done an exclusion in this area, for example, that can be a way. Something that will avoid the salts to enter, but it's not easy, and they don't exist. So internal concentration polarization is the main issue today for developing more and optimizing this forward osmosis system for real industrial application. In principle, if you are able to solve the problem, and some people are trying to, the advantages is basically, remember, no hydraulic pressure, or very, very low. We don't need, we adjust, you can have just diffusion, given the different chemical potential. High rejection of wide range of contaminants, because you are using osmotic membrane, 99% selectivity for at least sodium chloride. High rejection, lower membrane fouling, because there is no convection to the membrane surface, and that is one of the interesting aspects. And relatively simple system. Nature is doing in such a way you don't notice nothing. When you go in front of the trees, there is a lot of this kind of phenomena. When you give the water to on the ground, shortly, if you look up, you will see at the end of each of the leaves a drop of water. What has been moving the water from the down in the ground 30 meters to the top? This kind of phenomenon. The trees is full of osmotic membranes, able to create a difference in keeping a different chemical potential, as if you just give fresh water against the salty concentration present in the trees, the water is going up. And that's what nature is doing, basically. And there's no pump, no noise, and you see the water arriving on the top. And that is a typical example of, but that is because the system is relatively simple, and there is no big pressure that has a lot of interesting consequences. If you want, however, to realize this, you have to develop new membranes with high permeability, high rejection for the solid, and find a way, that is the major point, to reduce concentration polarization. Think about, invent something, and that can be quite interesting because the prospective, because if you solve this problem, you have disadvantages that overcome also the problem of reverse osmosis. Reverse osmosis will lose competition if we solve this problem. You need high chemical stability, mechanical strength, and we have to produce better draw solution. Draw solution that require low energy for regeneration, because draw solution during the process you are diluting. So at the end of the story you have to find a way to remove the salts or to reconcentrate again the draw solutions, otherwise it would be a cost. It can be evaporation, or it can be, so you can separate by evaporation eventually, but so you are applying again reverse osmosis on the draw solution, and that is the energy balance that does not fit, except in emergency. Some of the system can operate in emergency. If you are alone in the middle of the ocean, if you have a piece of membranes and you want to drink with this kind of system, you can drink, basically. You have to find draw solution that are easily you can separate easily from the product, have a low, no toxicity, otherwise for sure you will not be able to drink again, and eventually don't interact with the polymeric, with the material forming the membrane to have high lifetime, etc. Which is not, again, on problem, not easy. Pressure retarded osmosis and reverse electrodialysis are, however, the two process that really can be utilized for producing energy. So these are the two one that no one is really suggesting today to have 20% of the possible blue energy tomorrow using forward osmosis for part of the reason I was telling, particularly for the problem of the concentration, internal concentration polarization. Vice versa, if you are working with what is called reverse electrodialysis, that's the one in which also we are working, or if you are working with pressure retarded osmosis, that apparently can be interesting. Why this? The reason for this is that people spend time in doing some calculation, and all around the world, not just today, but already in the past, and they observe that you can have a lot of energy is available in principle from mixing water streams with different salt concentration. Any kind of water stream, a river with seawater, lake water with river water, municipal wastewater. There is a lot of difference in salinity that normally we discharge with no control. If you put a membrane in between, we have a lot of Gibbs energy, delta G, that we can utilize. So that is always present, particularly when freshwater streams flow in the sea, or can be made available from natural or industrial salt brines. That means, as we discussed and mentioned, if you have desalination already running, there is a lot of salts with a lot of brine available. It's no brine disposal, but big opportunity if you want to produce energy. Somebody, student of your age, this is in the Netherlands, a few years ago, he made his thesis, work in this area, and there is a lot of data from him. He was very optimistic, he liked his work, and he was assuming that the output, that the amount of water, of energy available in principle is of this order of magnitude, huge, 2.6, 10 to 12 watts. And basically it represents 20% of the present worldwide energy demand. So that is not wrong. The possibility, however, to obtain all this energy is a little bit not so easy. Here's what we are talking about. So the electrochemical energy from brine, in principle, if you make your calculation, you can calculate the Gibbs energy of mixing fresh and salty, and as function of the concentration in the other compartment, you see here what you have. If you just have, this is the, when you have seawater is 0.5 molar, here we are, down here, assuming that the brine, the concentrate is roughly 1 molar. So that's relatively low. What is important here, that you can immediately see that if the concentration of the brine, not seawater is 0.5 molar, but already you go to 1 molar, double, or you go to 4 molar, 4 times more, or you go 1 order of magnitude, 5 molar, these numbers change a lot, following the equation that you already know. So that what is interesting today, that if you want really to realize all the potentiality that we have to try to operate at this level of concentration on the brine side. So that means we have to concentrate. That's why you will see that in many of the discussion we've been doing, if possible next week we will discuss this system, you have to combine, for example, membrane distillation with pressure retarded osmosis or with reverse electrodialysis for having brine, not down here, not going from 0.5 only to 1 or 1.5 etc. operating here, but up here. In this case, the fresh water against 6 molar will give much more energy than the one that people were calculating years ago. That was the basic idea. No one, membrane distillation was not existing, reversal was not existing, so there was no way to concentrate at a high level with, without spending too much money, basically. Today, we have this possibility. If you do this, you can have from the salinity gradient power, in principle, this is a 2.6 huge amount of energy available. And that is the situation in which that has been attracting. What we are talking about, people have been doing this calculation. In nature, here there is this is the Amazonia, probably yes, this is Amazon estuary taken by NASA, and there is a lot of fresh water entering in the seawater. And this is all around the world. Can be the Columbia River in the United States, in Alaska, or in near Seattle, etc., or any other river, the Po River going the Adriatic Sea. That was, we made our experiment there. And you can find a lot of interesting situation. And already years ago, I was telling you this is not new, people already were trying to anticipate. It's quite interesting, and this can be done creating a power station here based on PRO or reverse electrodialysis. Potentiality again is quite interesting. This is not the only case of the estuary of the river going, because keep in mind that, for example, Dead Sea, that's the way to put the Dead Sea as a very high concentrate salt solution. It is one huge project, the Red Canal, to produce water having entering from the Red Sea, from Aqaba in here, and going to the Red Sea. And there is this level of difference of about 400 meters, which can be just utilized to create the pressure for the salt in the water. The only trouble in this way, you can eventually have a problem of a lot of political issue making this kind of program, which is already been analyzed and studied and realized in paper many times, however, still does not work. But I mean, it's not only the Amazonia River, there is a lot of this kind of opportunity. You can see here from seawater and to the concentrate of the traditional reverse osmosis to the Great Salt Lake, Dead Sea. This is in principle, the water ache, the different that you can create just if you put a membrane in between this kind of solution. So Dead Sea is quite interesting, and that's why there is this project that is in progress. But, for example, there is a lot of mining industry in which you have a lot of waste created at very high concentration. If you mix in fresh injected water from a vacuum salt mining industry, you have where there is a 15 high percent brine from a salt cover, you can gain is 15 megachow. So there is a lot, if you start to analyze the situation, there is a lot of interesting opportunities for realizing these things. Some power station, osmotic power station, have been installed already. More than one. The largest one was one, there is one company in Norway that has been introducing, that has been investing money. I have to also to say that recently they stopped operation. They lost a lot of money, and they decided it was not too good for them. StarCraft is the name. But it means that a lot of calculation was done, quite interesting, to the point that they decided this StarCraft is the largest energy company in Norway. So it was not just bankers, etc. People who made the calculation, that the system was quite attractive, to the point that they start to spend a lot of money and realizing power station, etc. However, also they have to survive, and the system still problem exists, and this problem has not been overcome as expected. So still a lot of work has to be done before big company will decide to continue to invest in this area. That is the system that one of these power stations has been created. You can see here all these people have been doing the calculation. In this case was this 1.5 megajoule, making the same amount of seawater with some cubic meter of river water. And this was just something of interest for them. There are two. There was one of these stations, in some cases, where price is not a problem. That means if you can clean the membranes frequently, stop the system, backwash, change the module, etc. If you go in the desert of Oman, in the middle of the desert where the sea is far away, etc., in some case you can use that. You have some brackish water, underground water, very salty, and you have some fresh water. You can recycle the water. In this case, the cost is not an issue. The same when you go in hospital and you find membrane for producing enriched air or in oxygen. Cost is not an issue. In this case, membranes are doing the job much better. It's interesting, however, in negative, that a lot of problem exists also in the public acceptance and visibility. If this is some data, statistical review on the energy tomorrow, this given by BP in 2011, a few years ago. And if you see here, they were considering everything no blue energy, zero. In the prediction of this big chemical company, petrochemical company, oil, coal, natural gas, nuclear, hydro, renewable, etc., but no, basically no blue energy. So we spent some time to fight with this guy a little bit and to redesign, we recalculated all this prediction, introducing the blue energy, and if you make this calculation, all these numbers change a little bit. The 33 is becoming 27, coal is going down, that's the most, coal is the one producing most part of the CO2 problem, and you can arrive to about 16.7% on the basis of the existing membranes. And how much this is compared in terms of cost, a different story, but not so dramatic to the point that some companies started to make the operation. So it's not something that in principle, if you are optimistic, that can give you some interesting result. Some people are also, again, he was making some assumption that in some case you can not only having 20%, but much more than this, and that is a little bit too optimistic. These are the flow sheet of the two systems. So pressure retarded osmosis, we understood already how it's going. You will have a system in which you are entering, on one side is fresh water, river, or lakes, or what it is. On the other side, we have seawater, and the membranes are in between. You just enter with the fresh water in the river, in the seawater. You pressurize the system. It's in a closed system. That means we're entering, you're growing with our hydrostatic column. And if this water is going with pressure, is going in a turbine, you just create the mechanical, you have your turbine running, so mechanical energy and electricity will be produced in your turbine. So that's exactly the system that is, you distribute the electron that you produce in the turbine just by the pressurization that you produce using the difference. Reverse electrodialysis is a totally different system. We never discussed with you about electrodialysis, but we mentioned a little bit also in a fuel cell. In electrodialysis, a process in which we have two electrodes where we can establish different in voltage. So the driving force is no pressure, in this case, no concentration different, it's just a delta different in the voltage between anodic and cathodic compartment. In between, you put different membranes, one cationic and one anionic. So you create this series of cells. And in this cell, there is one membrane is permeable only to to species with positive charge, and the other membranes are permeable only to species with negative charge. We learned discussing on fuel cell, for example, in fuel cell, that is membranes Nafion, where only protons can go across. There are membranes, this is a cationic membranes, but there are anionic membranes where only negative species can go across. So what you can do here, if you combine in an appropriate way the voltage across and the sequence of the membrane, look at this cell. In this cell you can have the concentrate solution entering. So there is a sodium and chlorine. Sodium, if the sign of the value is appropriate, will be attracted, will diffuse in this compartment, and the chlorine in the other compartment. So you have a situation in which you can extract sodium and chlorine from this compartment. Now, if you go in the other compartment, and look, the situation can be different, because you can have a system in which the chlorine does not go through, because this membrane is impermeable to chlorine, and the other one is impermeable to sodium. So you have basically a system in which you, in some compartment you concentrate, in some compartment you dilute. And that is electrodialysis, basically. Now, if you just collect all the solution coming from the compartment where you concentrate, and all the solution coming from the compartment where you dilute, you have fresh water on one side and concentrate water on the other one. In Japan, this system were invented. The membranes were produced in Japan, not for producing water, but for producing concentrate salt solution. In Japan, there is not nice sunshine every day, etc. Sodium chloride is a basic product for industrial production. This sodium chloride is now from sodium chloride by this chlorosoda process. You produce as the starting of chlorine and soda, which are the starting compound for any industrial system. So in Japan it was necessary, they invented these membranes and they were producing concentrate salt solution in this way. If you want to make a reverse electrodialysis, you don't need to apply here the voltage. You have a different, you can enter with very high concentrate solution on one side, very less concentrate on the other side. So these ions will diffuse across the membrane in the same logic, but by themselves, by a salinity gradient, basically. And they will accumulate positive on one side, and they will accumulate on the other one. Here you will have your catalyst inducing reaction, producing electrons, exactly as we saw in the fuel cell. So you will have at the end this electricity. If you just combine the electrons moving from one side to the other, and you just create this if you continuous supply of sodium chloride on one side and diluted, you just produce electrons by the oxidation and the reduction that you have in the anodic compartment and cathodic compartment. So we have reverse electrodialysis in this case, just because we don't want to split sodium chloride. We just diffuse across the same membranes on one side and the other, and we create at the end these electrons at the reaction. So exactly the same story, and the calculation on this one and this one roughly give you the same number in principle. The amount of energy that you can produce is exactly the same that you can produce with forward with pressure retarded osmosis in principle. So again, that is the same flow sheet, a little bit more extended, but you can see here what is happening. And then you have your turbine and generator of this of the pressure. You have your pressure exchanger. So this system is already been utilized and realized at industrial level, and it's nothing more than an osmotic system where you just operate in the condition we saw before with the appropriate delta pi, that is different than delta p, and lower, with no extraction of the water from the sea. With the existing membranes, however, this system is giving the performance I was mentioning before. Typically, you have, with assuming what I was mentioning, that the delta pi of the order 20-25 bar, which is is related to seawater brine, basically. The power density that you have at the end, the power density means watts per square meters, is measured in this unit, is between 0.11 and 122 watt per square meter. And so if you are increasing, however, the osmotic pressure, this number can increase. And that's what people are trying to do more and more. And you can arrive in a situation also where you can have from 2 to 5 watt per square meters. Initially, this was already when people started. But in this case, you can see here, you need to have delta pi that can be higher than 75 bar. That means the pressure you have to apply has to be significant if you want to have some effect. Recently, people have been working on different aspects of this seawater brine pair for pressure retarded osmosis, trying to solve the problem. And you can see here in a recent study, you can have a 2 molar draw solution to a new kind of draw solution that combine with seawater, 0.5 molar, just the seawater in this case. And in principle, if you make the calculation in this kind of situation, if you go back to slide number 1, I was showing you before, you can go up to about 4.7 watts per square meters, which is already progress compared to these traditional when you had just 1 or 1.5. These numbers every years, what is interesting, are changing and are changing in positive, because people are studying, as I told you, when the membranes are not completely doing the job you like, you can try to overcome some of the limits by some good engineering and try to see if you can minimize the problem and optimize the results by different design of the system. This is one case in which there are 1, 2, 3, 4 different integration of your PRO module with the turbine, a concentrated feed, and some pretreatment, etc. That can be one way of doing the number A, but you can also have system in which you have a reverse osmosis, and on the brine, on the reverse osmosis, you can have PRO. And this is another way of doing. In the alpha, you have your turbine, you have diluted draw solution, concentration feed. You can have also a case in which you can have the salination plant, a PRO, and combine different cases. What is here? The pretreatment, the difference between these two. Well, anyway, this is must be another kind of integration. What is changing is nothing. That seems to be duplicate of this one. But
that is RO here and
no, between this one and this one I mentioned. There's the desalination PRO, desalination. Oh, sorry.
Yes.
You're right. This is a RO plant, and this was a forward osmosis plant. So there's an integration of the reverse osmosis with the PRO module. There's integration of forward osmosis with the PRO module. So there is a lot of this possibility, and here there is not, but you can have other system in which we are working for them, in which there is, again, membrane distillation instead of PRO for increasing the concentration as much as possible using MD. Here is another case in which you have RO and FO working reverse osmosis and forward osmosis to optimize reverse osmosis, and after you go to PRO. So there are different kind of combination, and more than this. Because I said this is our 4, but we have students at ITM that already they have 7, 9 of this kind of different configuration, introducing, for example, the MD to increase the concentration before going to the PRO, so having much higher concentration in the brine. This is the same kind of configuration, and I will just in one of those you will see probably there is already MD, and but basically it's the same kind of concept where PRO basically can be combined in this case also with reverse electrodialysis or similar separation recovery, and you have in this case forward osmosis membranes are here and the PRO membranes basically are here. But just to give you that a lot of this combination can be done, and if you do this, you will have a lot of these plots. This is the same group of people I mentioned because Korean name are present. You have people working together with Hemi, with Elimelech, which has also been here in this here in Seoul in this same world-class university project in another university, and you can see in Korean people have been quickly working together, and you can check this water flux as a function of the hydraulic pressure and the change in the concentration 0.5 until 0.05, and you can have typical power density which is increasing or decreasing depending the pressure you apply. This is nothing more than rewriting the first slide number 3 that you saw before and making the calculation of the water flux possible to transform in power density for different delta P. And thus you have a lot of this nice plot. All this data, unfortunately, as I told you, when you go in real life, and here's the same story, you can have, as a function of concentration of the draw solution, you can increase in the concentration, and you have the feed concentration here at the power density. And you can see the changing the concentration of the feed solution and the concentration of the draw solution. You can have a quite significant change in power density from this value. Theoretically, by the way, keep in mind that when we are talking about the megaton, I mentioned about megaton project a couple of times, the people working megaton, which is a big group of industrial groups, they already are coming out last November in Tokyo with a value of the power density that you can reach, appropriate membranes, appropriate configuration of about 20. So some of these numbers here are not just theoretical, are just numbers that some company, real company producing membranes, big one, are assuming that can be obtained with a certain, and they obtain it in principle. A lot of effect have to be analyzed and studied that can improve the system. Temperature here, you can see here again that the power density can change and the water flux can change depending from the temperature. And increasing the temperature, you can have significant increasing from this value to this one. And that's because of the efficiency of the system. The membrane are always do the same job, but the overall efficiency of the system increases significantly, so you can have interesting that from increasing from 20 to 30 degrees, you can go from 9 to about 14 liters square meter per hour, and the power density is increasing from this value to this value here. So that is the way in which people are doing, and that is again the same kind of plot that summarizes what we saw before. There is compared to the introducing the power density in front of this water flux as function of the pressure. You can see here the region in which you can have interesting production or consumption of energy. There is area in which you consume energy, area where you produce energy. And that is just this conclusion that you can have from exactly the same plot that we saw before. So that is the influence of these osmotic phenomena in our life can be quite interesting. The real problem is always the one that I was mentioning before. Let's have a look, first of all, which kind of membranes has to be utilized. And this is interesting because these are some membranes showing that where people are trying to move on. And basically you have to find a system in which the spongy part is to be very porous as much as possible. In this case you can see here there's very high level of porosity and very, very thin skin. It's also losing mechanical properties. However, mechanical properties can be different from the one necessary for the reverse osmosis, just because the pressure that we are assuming are quite lower, and also the problem of if you are working with FO, with for osmosis, still less problem. Doing this way, with this kind of membranes, the 1.2 became 4.2, etc. Here, they're already 10.6 watt square meters, using seawater brine and wastewater brine as a draw feed solution, respectively. So slowly, people are making progress and approaching numbers which is not yet the 20 that we saw before, but approaching on the same line. And this is the same story with different level of concentration, how we can change this the plot significantly. reverse electrodialysis, very different in principle, no problem as the one we had in PRO, but different problems still exist. And the main problem here is in which there is a big project in Europe called REA Power, in which a lot of companies have been working together trying to arrive to some real prototype of a plant working on this high salinity we have in Sicily, in the south of Italy, where we produce salts using the sun. And this also we are very concentrated, they call saline, salt area, a lot of evaporation, and you have high concentrate salt solution. And we have one plant there with producing with some units, even at something as a 10 watt square meter at the moment, so large one. And that is the system that we have been describing already before. And theoretically, the value of the voltage from unloaded stack, what we call when we have been discussing for the open CV, is given by something that is nothing more than the Nernst equation. That's something that you know, and but that is the flow sheet that we have to consider. The problem I was mentioning here is not concentration, internal concentration polarization in principle. These membranes are not asymmetric, so you have to take care of it. But the problem are the one that we discussed exactly the same when discussing about fuel cell. Can be just a diffusion of the ions, can be boundary layer. It for sure is also the possibility for this membrane to operate. They have to be membranes with the transport number of the cations and anions, respectively, has to be as much as possible 1 to increase the efficiency, and not 0.5 as in the solution. The trouble is that if you remember the Donnan equation, the equation that is giving you the possibility to have exclusion of ions in the system, of the co-ions from the system, the basic final Donnan equation is related to the charge density of the membranes. And the system is effective when the charge density of the membranes is much higher than the concentration of the co-ions in the solution. So you must have a ratio at least more than 10, because for having an effective repulsion, exclusion of the ions from the solution. Now, all these membranes that were existing until now were done for traditional electrodialysis, where you're working with solution of a certain level of concentration, much lower than the one we are considering now. So the charge density at a certain value. Now, if you are working, as we try to work to increasing the numbers to solutions which are not seawater 0.5, not brine 1.5, but we want to work with 5 molar, 6 molar, the charge density of your membrane has to be much higher. So you have increased charge density. You have to increase sulfonation or carbonylation, what has to be done? Can be done, and the charge density can increase, but you're losing a lot in the mechanical properties. When you increase the level of sulfonation, you have a much more swelling. Water is attracted, you swell your membranes, mechanical properties are going down. These things have to work continuously for long. So this is a big problem, and people are working, big companies are working, to produce membranes specifically designed for reverse electrodialysis, so high conductivity, but good mechanical properties, trying to avoid the loss of mechanical properties given related to the swelling of the membranes, basically. The electrochemical potential normally that you have for single track is same order that I was mentioning before, 0.17 volts. That is the power density that you can extract from this voltage is 0.41 watt per square meter, exactly similar to the one we have been discussing for pressure retarded osmosis, basically. Not very interesting for industrial application. You can find in literature already a lot of optimistic analysis, just trying to show you what can be done. The same, I think, the same post. He was also trying to identify between PRO and between reverse electrodialysis which kind of system is more appropriate. So he arrived to some conclusion where it's better to combine brine and river water or sea and river water. That means whether you can have an efficiency related to sea and river water competitive with the one brine and river water between reverse electrodialysis, which is suitable for river water and sea water, and different than the other case. If you look to all the existing ion exchange membranes, the one that we can have to utilize in terms of the thickness, the charge density, the resistance, etc., there's not too much really appropriate for the kind of application we are discussing. Most of them have been designed, as I was mentioned before, for electrolysis and electrodialysis, as basically electrodeionization in some case, but these membranes don't have the charge density necessary if you want to work to obtain high power in the system, just working at a very high concentration. As I was mentioning, we are just, people are working in this kind of system that to try to optimize, again, exactly as we discussed when talking about fuel cell. You can see here how significant can be the way in which you create your stack, your cell. The spacer, for example, the way in which you just move your solution on the face of your permeate and concentrate side of your membrane to avoid, to control the different overpotential that we discussed in the fuel cell is quite effective. You can see here changing from 150 microns to 750, increasing the turbulence, basically, etc. You can have a quite significant decline in the power density. So this system has to be very well controlled and identify which one is the most interesting. That is the project I was mentioning, REA Power. And you can see here is a multinational project. Different countries have been working together. That's just for, and there's a two company, Kraton and Fujifilm, are expert in, everybody here is expert in membranes, but these two, Kraton in the United States of America and Fuji, that you're familiar to you by name, are just company making only membranes. So people are trying to redesign membrane for this kind of system. And not easy, for the reason that I was telling. I was just showing this because I like to show you, we discuss, when we are talking about fuel cell, the problem of how to characterize these membranes. And I was mentioning that one way, interesting way of doing is to study this system with not in direct current, but in alternate current, such a way that you can measure impedance and not just ohmic resistance. And that is important because if you're just working with this kind of system, you can have, by the way, this is the integrated I was mentioning before. All the flow sheet you saw before that the people have been doing until now were not considering membrane distillation combined the system. They were basically eventually forward osmosis combined with PRO, etc. We are assuming that the system can be optimized exactly as I was mentioning in desalination by all the pre-treatment to the RO is the membranes. You go to the RO, but from the concentrate of the RO you go in membrane distillation, and membrane distillation is increasing significantly the concentration for going to reverse electrodialysis and to produce electricity. On the other side, you can also produce from here, this brine part can produce crystals, as we learned already, but also you can have this electricity here. And again, there are a lot of advantages doing this way, and this is becoming a very traditional way of thinking today, not yet realized at industrial level, but it is becoming one of the way of doing. What is membrane distillation? You know already, so we can skip it. What I was going to show you, and we will close here, how significant can be the effect, for example, here in the on the voltage, and in the typical plot that you do in these electrochemical units. As function of temperature, you can change significantly this voltage current plot, And if you want to measure what is happening in the system, you can see, for example, here. This is the case in which you can see now the situation with the current density increasing the temperature from 25 to 50. And again, you can have an area where there is a quite interesting linear relationship, but depending from the temperature, you have this second part where you can split in between the different values quite significantly. And one way to measure also this is the place where we are doing the experiments, and this is a lot of salt is here. I was mentioning what is happening in our membranes now, and why it's interesting to work with impedance instead than just ohmic phenomena. Because what is happening here, that the membrane resistance, as we discussed also when talking about the fuel cell, is not just related to the charge density of your membranes. It's also related to all the interfacial phenomena. And you can have an analytical double layer in the fixed charge groups in ion exchange membrane attract ions having opposite charge on the membrane surface. And you form this double layer that can grow. And you can have this diffusion boundary layer resistance in the system. Ion has to move across, exactly as we discussed in fuel cell. Capacitance of the interfacial ionic charge at the membrane surface related to the double layer, etc. So if you want, and these numbers are not constant. These are function of time during your process, are function of the concentration, of the charge density, of the temperature, etc., plus time. And it's because they are related to the transport of cations and anions in the system. And what is happening is that if you measure with this impedance spectroscopy, you can see only with impedance spectroscopy this kind of phenomena here. That's the one that we have. For example, if you at a certain frequency and a certain level, you have this membrane resistance, which is basically constant for any velocity, for any flow rate you're measuring. But when you're just increasing the flow rate on the system at a certain frequency in the system, and the diffusion boundary layer is the one that a very low, in this case, frequency, diffusion boundary layer can have a significant effect. And you don't see, normally, if you're making a direct contact, you don't see nothing. Here you see how effective it can be. That means how you can change the diffusion boundary layer, but just by changing the flow dynamic condition on your membranes. And that is one of the areas where people have to work today for learning what is fouling. This is a way to see the fouling. You see the fouling growing with time, because this phenomenon now is a certain moment, but if you just watch, you see how when these things are changing, you are changing the boundary layer and you are changing the voltage or the current that can be present in the system. The other problem, quite interesting in terms of fouling, is plotted here, and you can have also here some scaling. What's interesting is that the scaling can be quite selective and different from the one you have normally in traditional RO or NF. For example, here you see you can have a formation depending from how the system is done. You can precipitate calcium or something different. We observe, however, that you must be careful for depending from roughness, by the way, the roughness of your membrane can change significantly. Increasing the roughness, you can have a density of the calcium carbonate that is formed changing significantly. But what is more important, and is related to what I was mentioning before, if you have magnesium ions, which are present in the seawater significantly, you can have increasing concentration, you can have dramatic decline in the ion exchange capacity of your membranes. And that means because probably there is a specific interaction of this kind of ions, magnesium, with the charge density of your membranes, with the chemistry of the system producing the high level of charge density. And so the information you have studied in this way, that you have to eliminate magnesium. And that is new. We are publishing this kind of things recently because people are looking, we were looking, how to concentrate magnesium here, and we learn that we have to remove magnesium, otherwise we don't have the power density we are looking for. If you know it's not a big problem, you can separate magnesium, but for the moment it's magnesium, you have to check if barium or strontium, other bivalent or trivalent can give the same problem, with a typical problem of interaction of some of the ions with the charge density of the ion exchange membranes. Quite interesting now that we know, but unknown, so you have to take care of this. To conclude, blue energy exists, is one form of energy available that people were not considering in real life until now. In the future will be more and more analyzed. At the moment, two ways of doing is reverse electrodialysis or pressure retarded osmosis, basically. Forget forward osmosis, eventually only for pre-treatment to RO to clean the water. Both systems have problems. PRO basically is internal concentration polarization of the membrane that we are using, asymmetric membranes. The same problem does not exist, and everybody was looking to reverse electrodialysis assuming no concentration polarization. We don't have internal concentration polarization. We have other kind of problem, the same that exists in fuel cell as interfacial phenomena eventually instead of the wetting that we have in membrane distillation where the membrane lose property, here we have a blocking of the charge density by interaction with some cations or anions, we don't know, but at the moment cations, magnesium, a typical case, with the membranes. So the ionic conductivity of membranes is going down and we want to go up again. So you have to find a way or to pre-treat and to remove what is creating the problem, or to find a way to minimize this interaction. A lot of research has to be done, but it makes sense because the conclusion can be that you have potential huge amount of energy available that no one is using today. It's no solar, no wind, no nuclear, no coal, no oil, just mixing fresh water as nobody is using human beings. Nature is using on a large scale, and so it can be done if you're able to understand more and to realize what nature is doing. Okay, question, problems? You will receive, did you receive already the material?
Yes.
Okay. And okay, we will meet next Wednesday. Okay.